Hello everyone and welcome to our final presentation on optimization of HVAC system for auditorium energy efficiency and occupant comfort. This project explores a comprehensive multi-objective optimization approach to designing an energy efficient and thermally comfortable HVAC system tailored to an auditorium settings. Let's dive in. Our project objective is to minimize the total annual energy consumption of the HVAC system while maximizing the thermal comfort for occupants. To achieve this, we optimize architectural design parameters like wall insulation and window size, operational parameters like temperature, humidity set points, and comfort metrics using Fangus equations for PMV and PPD. The system includes three subsystems: design cost optimization, energy consumption minimization, and thermal comfort maximization. Our system boundary covers the HVAC equipment, building envelope, and control system, excluding structural elements. This integrated optimization framework is necessary to capture trade offs between cost, performance, and comfort that would otherwise be missed in isolated subsystem designs. This diagram shows the interaction between our three subsystems. The shared design variables are cooling and heating set points, relative humidity set point, and supply airflow. Subsystem 2's energy consumption feeds into the cost model of Subsystem 1, while all subsystems contribute to occupant comfort in Subsystem 3. Subsystem 1 receives energy consumption as an input from Subsystem 2 and includes that in its cost function. Subsystem 3 uses set points from Subsystem 2 to compute thermal comfort. These interdependencies make it clear that a system level optimization is essential to balance competing priorities across cost, energy, and comfort.
In Subsystem 1, the goal is to minimize design cost. Our design variables are wall thickness and window area. The cost function includes the energy consumption cost, cost of wall material, and an aesthetic penalty for deviation from the desired window area. Constraints ensure the wall thickness is between 0.02 and 0.08 meters and the window area stays above 10 square meters, but below the desired value. Modeling uses simplified heat transfer calculations for wall and window conduction. We used genetic annealing, implementing in MATLAB's optimization toolbox due to its robustness in handling discontinuities. This table shows the results from 6 trials. For example, trial 6 with 0.06 meter wall thickness and 50 meter square wall window area resulted in the lowest cost despite moderate energy consumption. As wall thickness increased, energy use dropped, but material cost began overweighing energy savings beyond a certain point. From these results, we observe diminishing returns beyond 0.06 meter wall thickness. While insulating initially reduced HVAC load, higher material cost eventually dominated. Small window areas reduce thermal loads but incur aesthetic penalties, increasing cost. Thus, design with large windows despite higher HVAC loads can actually lower the total cost. The subsystem effectively captures architectural trade-offs between aesthetics, material use, and energy consumption. In Subsystem 2, our objective is to minimize the total annual HVAC energy consumption. We optimize cooling and heating set points RH and supply airflow, constrained with practical bounds. The model uses hourly HVAC load calculations under sinusoidal weather patterns to capture seasonal effects. It considers conduction, ventilation, and both sensible and latent thermal loads. We implemented a genetic algorithm using MATLAB's GA function with a population size of 100 and 100 generations. We achieved a minimum energy use of approximately 109,798 kilowatt hours. Optimal set points were at their bounds: 26 degrees Celsius for cooling, 18 for heating, and 30% RH for around 2514 liters per second of airflow. This shows the optimizer favored the energy saving extremes.
On this slide, we can see the result of the optimization of Subsystem 2, where we reduced the total annual HVAC energy consumption to 109,798 kilowatt hours. The optimizer prioritized energy savings by pushing set points to the limits. Lower humidity and wider temperature ranges helped reduce HVAC load, but may reduce comfort. These results highlight the trade-off between comfort and efficiency. They also provide a strong reference for system-level optimization where we integrate comfort and cost metrics. On this slide, we are going to look into subsystem 3. Basically, subsystem 3 focuses on minimizing thermal discomfort, quantified as average annual PPD using Fanger's PMV model. The same four design variables used in the previous subsystem were used, and we modeled thermal comfort over 8,760 hours annually, factoring in air velocity and sinusoidal outdoor temperature. The optimization again used in this case was the genetic algorithm for consistent convergence behavior. On this slide, we see that we successfully reduced PPD to 5%, achieving excellent occupant comfort. The GA converged in 350 generations with progressive improvements across runs. This result confirms that well-balanced HVAC control systems settings can meet thermal expectations all year round. The results of the optimization of subsystem 3, where we see that the PPD was reduced to 5%, and this result shows that an increased airflow and relative humidity enhance comfort but come with some energy penalties. By staying near 45 to 50% relative humidity and adjusting airflow moderately, the system avoids overventilation and maintains thermal balance. The comfort model captures seasonal variation showing year-round performance. This subsystem demonstrates the importance of coupling thermal metrics to energy models in a system-level design.
Slide, we show a system-level optimization approach, which integrates all 6 design variables: cooling and heating set points, humidity set point, supply airflow, wall thickness, and window area into a multi-objective Pareto framework. The objective is to minimize total cost and average annual PPD simultaneously, reflecting both economic and comfort goals.
At the system level, we use a sinusoidal approximation for outside temperature and relative humidity to simulate seasonal changes. Then, we combine humidity ratio calculations with conduction through walls and windows and occupant loads to estimate the cooling energy demand. This holistic approach gives a realistic annual performance estimate. We calculate the heating load by accounting for heat conduction through walls and windows, plus occupant and lighting loads. We also include humidification or dehumidification by comparing the target humidity with outside conditions to find the water added or removed. These elements give us a comprehensive view of year-round heating energy demands and moisture control. To capture occupant comfort, we use Fanger's PMV model, which depends on factors like metabolic rate, clothing level, and indoor air properties. The resulting PPD quantifies how many people might feel thermally dissatisfied. Meanwhile, cost is modeled as energy expenses plus construction and aesthetic costs for walls and windows, ensuring we balance comfort, energy, and design considerations. In our model, we assume a perfect sinusoidal profile for outdoor temperature and humidity, ignoring daily extremes. We also fix heating and cooling COP values along with constant occupant, metabolic, and clothing rates. Finally, we keep cost relationships simplified and linear, ensuring a manageable model while capturing core seasonal trends.
This slide outlines the mathematical modeling steps at the system level. We started by initializing 6 design variables within defined bounds and optimized them using the GA multi-objective function to handle conflicting objectives. To simulate seasonal variation, synthetic hourly temperatures and humidity profiles were generated using sinusoidal functions of Ann Arbor. Cooling, heating, conduction, and fan energy loads were then calculated based on outdoor temperature and airflow. Thermal comfort was modeled using PMV, which was converted to PPD, and total cost included energy, construction, and aesthetic penalties calculated iteratively. Finally, results were graphs showing optimal parameters in metrics X and cost PPD trade-off through FVAL. Using MATLAB's GA multi-objective, which implements the NSGA2 algorithm, we generate a set of Pareto optimal solutions. The table at right shows various combinations of set points and design parameters along with their corresponding cost and PPD values. This visualizes the trade-off clearly, letting designers pick the balance of efficiency and comfort that best suits their priorities. Graph shows the Pareto trend representing the trade-off between total cost and average PPD or thermal discomfort. We can see that the cost increases slightly, the PPD drops, indicating better comfort points and representing optimal solutions balancing both objectives. This shows the progression across generations. At 5 generations, the front is sparse and scattered, By 20 generation, a clearer trend emerges. At 40 and 60 generations, we get a more refined Pareto trend, showing how the generic algorithm converges towards optimal solutions over time.
For post-optimality sensitivity analysis, we conduct two parametric studies, one for the parameter sensitivity and one for constraint sensitivity. We perturb the parameters by a 10% value and record a change in the objective functions and report sensitivity accordingly. So for cost wall thickness, uh, we started off with a value of 5 $5, and then we perturb it by 10%, making it 5.5, and then we check the whole system, and then we report the sensitivity. For constraint sensitivity, we have upper and lower bound constraints on this problem, and we perturb these by 10% as well. Through sensitivity analysis, we can see that the objective function values don't blow up on giving tiny perturbations. This whole system level optimization gives us a trade-off between two conflicting extremes of cost minimization and increase in thermal effort. For future work, we would like to use thorough CFD calculations and feed that data into maybe an AI and use that AI model inside of our subsystem to give more accuracy and better representation. To conclude, we can see that this optimization framework effectively balances construction cost, energy efficiency, and occupant comfort by tuning our six decision variables. For extension and improvement, we can incorporate real-world weather data and replace the sinusoidal approximations that we were using in the subsystems. Also, we aim to reduce sensitivity between parameters and constraints by refining the model structure more and adding it more robustness and stability.